All designs are created from entities. Here is the basic structure for an entity declaration. The keyword entity begins the entity statement. The name of the entity follows the keyword. The line ends with the keyword is. An entity consists of two sections, the generic declarations and the port declarations. Generic declarations are used to pass information into the model. The port declaration section describes the inputs and outputs to the entity. There are several ways to close the entity depending on what your preference is and what version of VHDL you are trying to support. The port declaration is used to declare the I/O to your entity and occurs within the entity declaration after the generic declaration. Similar to the generic declaration, the port declaration starts with the keyword port and then, within parentheses, lists all of the I/O. It ends with a semicolon. The structure for a port declaration goes class, object name, colon, mode, and then type. The class is most always signal, though it doesn't have to be, so you almost never see the word signal actually appear in a port declaration. The object name is the name of the I/O port. In this example, the object names are clock, clear, and queue. Since clock and clear are of the same type, they are declared together, separated by a comma. The mode is the direction of the port. In VHDL, the keywords for directions are in for input, out for output, in out for bidirectional, and buffer for an output with internal feedback. Typically, input signals can only be read from and not written to. Outputs can only be written to, not read from. In-outs must be used as both inputs and outputs. With buffers, physically in the device you will have an output pin, but you'll be allowed to read from it as well. Use care when using buffers, as there are restrictions on them when connecting them to other design blocks hierarchically. Personally, I stick with in, out, and in, out. And lastly, the type is a data type that defines the type or values that can be held by your I/O. Like the generic declaration, the semicolon is used as a separator, and the last port declared is not followed by a semicolon, as you can see after the word bit for the Q port. Generics are values that could be passed into an entity at compilation time. We use them to make our entities parameterizable when designing hierarchically. The generic declaration is contained inside of the entity declaration. We use the keyword generic and within parentheses list the generics. The format for a generic declaration goes class, object name, type, and initial value. The class signifies what can be done to the generic. Generics are almost always constants, and the keyword constant is usually left out. The object name is the name of the generic that will be used within your model. The type is the data type, which specifies the values that your generic can hold. Finally, the initial value is optional. As you can see in the example, the generic declaration is itself considered a statement and ends with a semicolon. Within the parentheses, the generics are listed with semicolons separating each one. Since the semicolon is used to separate the list, there is no semicolon after the last generic, as you can see after the word up. Also notice you can declare multiple generics in one line if they are the same type and initial value by using the comma. Thus, TPLH and TPHL are both generics of type time initialized to 5 nanoseconds, and TPHZ and TPLZ are both generics of time initialized to 3 nanoseconds. The architecture describes the internal logic to your model, analogous to a design schematic. While the outside world can see the entity name, the parameters being passed to it, and the port connections, it cannot see the actual guts of the block. We use the architecture to describe the functionality and possibly the timing of the model. Architectures must be associated with an entity, but an entity can have multiple architectures associated with it. This is done sometimes in simulation when a designer wants to use two different sets of test vectors to test the design. He or she may have two architectures and will select one at compile time. Multiple architectures may also be used by designers when they have one architecture that contains a synthesizable model and another architecture that contains a simulatable model. Depending on what action they are performing, be it synthesis or simulation, they will select the appropriate architecture. Within an architecture are implied and explicit processes that execute concurrently. We'll be discussing processes in a bit. When coding an architecture, there are two methods that can be used: behavioral, with the design described with an RTL and functional coding style; structural, which connects gates and components together like a netlist or a mixture of both. Similar to the entity block, the architecture can be terminated with several different methods depending on which version of VHDL you are supporting. The architecture starts with the keyword architecture. Following that is the name of the architecture. You can use any alphanumeric name for your architecture. In fact, many designers, including myself, will simply reuse the same name for all of their architectures or most of their architectures. Since architectures are invisible to the outside world, reusing the same name is not an issue. If you have multiple architectures for the same entity, then the names must be unique. After the architecture name, you have the keyword of, and then the name of the entity that this architecture belongs to, followed by the keyword is. Then you have the architecture declaration section. Local identifiers that you use inside of the architecture that are not ports or generics must be declared in the architecture declaration section before they can be used in the design. In this example, we see that we have a constant, a signal, and an enumerated data type. All of these we'll talk about in more detail later. After the declaration section, you have the keyword begin, followed by the architecture body. The architecture body contains the executable lines of code within the design, made up of various types of processes. End your architecture with the line end architecture and then the architecture name. Notice the formatting of the architecture shown in this diagram as well. By using proper formatting like this, your architectures are much easier to read. As you can see, the architecture declaration section is indented, whereas the begin and the end architecture are in line with the keyword architecture. The third design unit, the configuration, is used to associate an entity to an architecture. Since entities can have more than one architecture associated with them, the configuration assigns a unique name to a single entity architecture pairing. Then, instead of having to choose a pair, you simply select the configuration name and the tool understands which entity architecture pair you are referring to. While they are supported in synthesis environments, they are used more so in simulation environments where, again, I may have multiple sets of test vectors applied to the same entity. The format for a configuration starts with the keyword configuration, then the configuration name, followed by of, and then the entity name, is for, the architecture name, and then end for. You end your configuration with the keywords end configuration and then the configuration name. As a note, in hierarchical design, you can also use configurations to associate lower level components in an entity architecture structure. Here you can see an entity, an architecture, and a configuration all working together. The entity defines the ports. In this example, A, B, and SEL are inputs, and X, Y, and Z are outputs. The architecture defines three muxes. You can see that the three muxes are encoded using three different styles: a simple signal assignment, a conditional signal assignment, and a selected signal assignment. We will look at these assignments in detail later in the presentation. Finally, the configuration ties the architecture and entity together. Once again, configurations are typically